everyone. I'm Jong-Hyeok from SunMoon University in South Korea. We have developed the best coding algorithm for HEVC. So we have used skin mode information and CO correlation. I will introduce simply and previous best scheme, followed by the proposed best scheme, and then experimental result and conclusions. So, market demands for video services with increasingly high quality continue to be evident. So, according to various reports, so Ultra HD video is expected to emerging in the near future and will be supported by next generation displays and data rates for video contents also are increasing faster than the network infrastructure it is being able to carry economically. So MPEG and PPEG was developed the HEVC on officially called H.265. So I think a major feature when the HEVC compared with the H.264, it is coding structure. In this structure, there are three units. As well, coding unit and prediction unit and transform unit. Coding unit is base unit for region splitting, and then PU is used for prediction process, and Q is used the transform and quantization process. Encoding unit structure performs recursive splitting into 4 equally sized blocks. So, figure 1 shows the CU processing order in CU in recursive structure. It may take a size from size of smallest coding unit SCU up to size of largest coding unit LCU. So it is always spare. And in prediction mode, there are 11 variable modes, and skip and intra and intro. So figure 2 shows the CU decision and variable modes in intra and intro prediction in HEVC version. So because these variable modes, so the HEVC has a high computational complexity. So important point is how to exterminate sub-tree computations in quad-tree structure. In this slide, I will explain previous approaches simply. So, in there are 2 methods in seventh meeting, and then coded block flag to reduce the computational complexity. And then ECU is used mode information if best mode of current CU is skim mode, so sub CU is omit. And then ESD is early skip detection algorithm. They use the skip condition, 3 skip conditions in H.264. So we have developed also fast CU decision. Then I will explain here in next slide. So we made more fast CU decision, so we use early skip termination. In early CU termination, so it is based on potential of the current CU and its sub CU. And then to prevent a large loss of video quality, so we use mode information about skim mode. So and then we make more fast encoding system. So we developed the depth range selection mechanism. So this mechanism is to decide starting from which depth in the LCU in order to achieve even greater reduction. So this DRSM analysis of current CU in depth level X, and then other depths, other old CUs or CUs correlation by using skim mode. Figure 3 shows the probability of skim mode of current CU in depth level X. It is skim mode, and sub CU is skim mode probability. So when current CU is skim mode, its sub CU is skim mode, the probability is very high, it's more than 90%. So we use this skim mode. So if let's explain this, right? And then so we more analysis. So in correlation of CUs in LCU, so we were tested. So figure 4 shows when the current splitting CU is skim mode, the probability of skim mode in other depths, other words CUs, is skim. Other words CUs. So red bar means 16 by 60 current CU is skim mode when upper parent depth is CU and child depth is CU is skim mode. So probability. So current CU's best mode is skim mode. So in other CUs in same depth level, is skin mode probability of skin mode is high, and sub-CU is also high. So, and in upper depth, parent depth, it is some probability. There are some probability. So we will design the DRSM. It is current CU in depth level X is skin mode. So each depth level -1 and +1 is applied. So, this is example for our mechanism. So first, let's see this part. This part is applied to RSU combination. So if this CU is skin mode, so we terminate the sub-CU calculate sub-CU processing, and then so I will explain the first step. This is first step. If this CU is best mode of this CU is skin mode, so we determine the DRSM is this CU's depth. So, and then we apply the depth level -1 and +2. So we will also check the depth level each series. So if DRSM is determined to 3, so next CU processing in depth level 1, it is just jumping skip. And then so each sub-CUs this CU has depth level 2, so it is included in depth level -1. So starting from this depth. So and then apply the and then processing all CUs, it is apply the early CU termination. So if this best CU if this processing at the best mode is skip, so terminate the sub-CUs. So we was tested in environment, so in HEVC version, and then all tested in random access mail, and then all sequences. So this is just to appear delta bit and delta YPSNR and delta time. So we was paired with ECU algorithm. So we have some very similar with reference software, and then but this ECU algorithm have some game with iterative and YPSNR. So we need to do similar, and then time is our proposal is some high, almost 45%. So and then we was checked in standard template. So saving, so it uses geometric means. So some difference, but time saving is high, also high. So some ECU has bit rate loss almost 0.4, but our algorithm has 1.2 of bit rate loss. So some, and then time saving is 48%. So our proposed algorithm gives less amount of bit rate, so within very marginal PSNR loss. And then our method achieves 48% of time saving on average. The ECU average gives 44% of time saving. The proposed average for early termination, we use the scheme mode, and then for more removing unnecessary sub-tree processing, so we will design the DRSM using scheme mode. So the experimental results, we compared other algorithm, ECU, to evaluate for performance, and then our algorithm achieve 48% time saving on average. But in the bit rate aspect, so our algorithm has some loss, almost 42 of bit rate loss. So, do you have a question?
Okay, so thank you, Mr. Lee. Are there any questions in the audience? Not a single one? Okay, so I was just wondering about the numbers, but initially you stated on the results slide, I guess on slide 15, yeah, maybe 14, yeah, that you're saving up to 45% in overall encoding time without sacrificing any quality.
Maybe.
No, okay. The left one is the work choice. I'm sorry, I guess I just moved the numbers up. Okay, but anyway, so if I got it right, your work heavily relies on the quad tree structure of the prediction units.
Yes.
Yes. Okay. At least this. Are there any ideas how to apply to some non-symmetric prediction units?
Yeah. So we want to just use scheme mode. So other prediction mode is expected. Performance is same thing, but one more. Yes.
Should I explain it once again, or the question once again, or? Okay. Yeah, I guess it's kind of a misleading question because you are relying on this quad tree structure, and my question was: is there some similar thing you can apply to non-symmetric PDs? Okay, so it's not a problem if you don't know about it. Okay, so yeah, let's thank again for the talk.